about the homework before we start officially, though. Let me get the recording started. So just a couple tidbits about your homework. So we got through this last one, which is similar to the last question on your homework last time. Just note that WebWork uses X's instead of Q's a lot because for some reason WebWork just cannot handle Q's as answers. The large majority of these questions I do not write, but I was trying to write my own questions and trying to have it accept Q as an answer, and it just wasn't working for some reason. So just be aware of when it tells you to use a different variable than we're used to. Here we're using Q's, and in WebWork it uses X's more often than not. One thing that I've gotten a couple questions on, make sure that when you're doing questions where you have multiple points and you're trying to find the equation, that you're setting it up correctly. So be really careful to look out for that phrasing. Like in this question that we did the other day, it was, what is the demand function in terms of the price? So that was essentially what was telling us that Q equaled F of P as opposed to P equals F of Q. So there's always going to be that type of phrasing to tell you kind of how to set it up, which ones are going to act as your X's and which one are going to act as your Y's. The other thing that I sent out an email about this, but just to triple check that everyone knows, which I was not aware of, is that WebWork requires, I guess, 3 decimal points to accept the answer. I don't know why. I don't know how we were supposed to know this. I think I've mentioned this a few times. This is my first official time using WebWork in this capacity, so there are probably going to be a few little bumps here and there that I'm not aware of in terms of WebWork and what it accepts. But WebWork apparently needs 3 decimal places unless otherwise specified to accept the answer. I had a couple people with emails that said, hey, I can't figure out the answer, and their answer was technically correct. They just had 2 decimal places instead of 3. So just make sure if something's really bugging you and you're pretty gosh darn sure that your answer is right, make sure you've got 3 decimal places, not 2. Otherwise, as always, feel free to email me and let me know, because I can always try to figure it out. Anyway, so that's due tonight. Your next one will be up later today, and we're gonna jump in here. So to remind ourselves what we're doing here, because this problem is gonna continue, is we've essentially got this this woman Anne Marie, and she's selling dog biscuits. And in the first question, we found the demand equation in terms of price. So we essentially, and the big piece of this moving forward is that now we have a relationship between Q and P. We have some Q equals this equation. And so we found that equation for demand, and we used it to find our revenue function. So since revenue is P times Q, and we now knew what Q equaled, we could replace that in. So now we're at a point where we're going to focus on the rest of the equation. So we found our revenue. So now to go global, she has a fixed cost. My laptop's angry. Hold on one second. She has a fixed cost of $10,000 and a marginal cost of $2 per biscuit. Express the cost C of producing Q biscuits. Is it happy again? There we go. So C of Q would be, remember, cost is fixed plus marginal, and the marginal is the one that has the variable attached to it. So we have our 10,000 plus 2Q as our cost equation. Oh, yep, hold on. Let me reshare. Because, yep, you should definitely see the problems up. And technically, you should see me too, but that's not really as important. Just a little tiny thing at the bottom of the screen. So I'll leave that up for a couple seconds. So 10,000 plus 2Q. So that's our cost equation. In a second, I'll scroll down. I didn't need to put this much space between these questions, but I did. So our next thing is that using parts A and C, so let me remind us what those 2 parts are. The part A was our demand equation, so that was our negative 55.44p plus 37.820, and part C was essentially what we just found, our cost function in terms of quantity. So those are the 2 pieces we're going to need for this question. Express the total cost of Anne Marie's operation C in terms of the price. So essentially we found the cost equation in terms of quantity, and now we want to change it over to a cost function in terms of price. So now I'm going to write it as C of P instead of C of Q because we want it in terms of price. And essentially what we're going to do is we're going to take that cost equation that was in terms of quantity and replace that Q value with what we know it to be equal to based off of the demand equation. So almost exactly what we did with revenue, where we replaced the Q value with the function, same deal here. And then we'll want to expand this and simplify it a little bit. So we'll distribute this 2, which will give us something. Negative 11,088 P plus 75,640. As always, I go through these calculations a little quick because I trust to believe we could type it into a calculator. But if you're ever confused about where something's coming from, just stop me. And then we can combine together the two constant terms to give us 85,640 minus 11,088 P to be our cost equation in terms of price now. I'm just going to take a second to remind us what we need for this one. So this one is, we need the thing we just did, and then we need, so you don't need to write that down if you don't need it, but just to remind us what the pieces are that this question is asking us to pull on. Okay. Questions about that cost question? Okay. So now we're asked to essentially use parts B and D. So part B was the revenue and part D is what we just found, to express the total profit in terms of price of each biscuit. So we want the profit function in terms of price. So remember, profit is our revenue minus cost. And we want it in terms of price. So we want to use the ones in terms of price for each case. So we have the negative 5544 P squared plus 37,820 P minus, always put your cost function in parentheses to make sure you distribute the negative correctly. So we will want to distribute that negative. Usually I would skip this intermediate step and just jump to the answer, but I'll write it out just in case. And the only thing to combine together here is the values that both have just a singular P in them. Everything else needs to stay separate. So if we add those together, we will get 48,908 P minus 85,640 as our profit function. Questions, concerns on that? Okay. So our last piece is we're asked to use the calculator to graph the profit function we found in part G and find the vertex. What price should Anne-Marie make each biscuit to maximize profit? So what I want to do real quick. 1 second, that's going to look really stupid for a minute until I fix this. No, I didn't want to do that yet. Darn it. And then I'll just zoom out in case people need the equations. So because we're online, you can, of course, use the internet. So instead of showing this to you, well, I don't have the thing set up to show it to you on my handheld. So if you have a handheld graphing calculator and you know how to graph on a graphing calculator, go right ahead and use that. Otherwise, one of the acceptable online calculators is Desmos. So note on exams and quizzes that you're only allowed to use Desmos or GeoGebra. Those are the two ones that don't do more than I want them to. So math tool. So it's got a scientific one. It's also got a graphing one. The graphing one can also handle like the scientific stuff if you just do like what is 3 plus 4 and it'll tell you it's 7. But anyway, so if we want to graph this, we just type that out. Now the only thing with Desmos is that you're going to want to use X and Y's. Why didn't I type that out fully? You're going to want to use X's and Y's instead of any other variable, or else it's going to, you can, there's a way to get it to work with other variables, but it's not worth the effort. So if we wanted to graph this guy, we would type that out, and then we can hit this to make that go away. Now to find the vertex, I don't see it. So one thing with Desmos is you can literally scroll out, but if I scroll out, that's still not helping me, and now it's like I barely see anything in what is happening. So let's leave it scrolled in a little bit. And what you can do instead, if scrolling doesn't work, is you hit this little button up here, and then you can just like change the numbers you want it to go between. So I'm going to go from -3, and let's try to bring that in a bit more. So maybe 40, so I can, nope, that's too much still. What if I want to just, I want to see both sides. 10's enough to get both pieces of that. So I get both pieces there, but now I need to really extend the y-axis because I can't see that vertex yet. So I already know what it's going to be because I just did it in my last class. But let's say I didn't know what it was, and I was like, well, maybe 100 will work. And I still don't see the top. So maybe 1,000, and I still don't see the top. So then you can just keep, trying. Still don't see it. How about 20,000? Almost there, but not quite. And I think 25 is the thing that worked. There we go. And you can keep changing those around to try to fit the thing into how you need it. Most of the stuff we deal with, that doesn't take that much work. But if you're trying to work with Desmos and move things out like that, that'll work. If you're doing this on a graphing calculator, it'll probably take a bit more time because you have to change the window every time. And if you don't know the window right away, then you're going to have to guess and check, and it takes longer than what I just did on Desmos. Now, the other nice thing about Desmos, if you just click on the function, I need to extend this down a tiny bit past, oh, it does. Well, go down a bit further. Oh, sorry, -20 is what I want. No? Okay, maybe more because I need to see it. A bunch? There we go. Just wanted to see the x-axis. The nice thing about Desmos is when you click on the function, it pretty much points out points of interest. So all of the intercepts will show up, and actually it does pull out the vertex for us. So Desmos is honestly probably the easier option. Since you're allowed to use it, I would almost use it over my handheld because it's just easy to do. But if you have a handheld calculator, you can do that as well. With a handheld calculator, I'll remind you real quick if you don't know how to do it. So if you have a handheld calculator and you have it graphed, this would be a TI-84 or 83. You would hit the second button and then the trace button. And then you would select option 4 for maximum. That's only if you can actually see the maximum. So you would still have to somehow zoom out to be able to get that vertex in the picture. But then what you do is essentially asks you to pick a point to the left of the maximum, to the right of the maximum, and then guess. And then it'll tell you which one it is. If you want more information on that, I can give you more information, like some pictures and stuff, so it makes more sense. But honestly, Desmos is a pretty solid choice there. Anyway, so our vertex looks to be 4.411 and then 22,224.018. Now, I want to talk really quickly. Yes, we already found the vertex, but I just want to go over one other way you could find it. Let me make Desmos go away. Let me just bring this back to just the notes. And so if you want to do this one more way, you can also find the vertex algebraically. So if we have some ax squared plus bx plus c, or whatever variable you need, then to find the vertex, the x value, in this case would be our p value, is going to be at the coordinate -b/2a. Well, that's going to be the x coordinate of the vertex. So in our case, it would be -48908 over 2 times -5544. Now, if you do that, it doesn't come out to be exactly what Desmos gave us. It comes out to be 4.41089 blah, 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 blah. So obviously it rounds up to what Desmos told us. And then if you wanted the actual other value, you would need to plug this back in. You would have to plug that back into the profit function. Now, technically, what the heck is the actual answer to this question? I haven't actually answered it yet. not fully. So what this was asking was, what price should Anne-Marie make the biscuit to maximize profit? So all we needed was the price. So technically all we needed was the p-value. So we only needed the 4.41. So the answer to this question was that she should charge $4.41 per biscuit if she wants to maximize her profit. That $22,224 is the maximum profit. We didn't need it here necessarily, but it was easy enough to find on Desmos, so I wrote it down too. So 3 different ways you can find the vertex. I personally just think Desmos is great, so feel free to use Desmos if you like it. Questions, concerns? Questions, concerns about this section in general, because at this point we're done, because remember the extra problem I will have filled out on Blackboard, but we're not going to do that together. You can do that for extra practice if you want. So questions, concerns about this section before we move on to the next one. This would also be the time to go grab those notes if you don't have them yet. Okay, I'll leave this up for a couple more seconds. Also, as we're getting ready to start this new set of notes, note that your first exam is next Wednesday. So that's not 2 days from now, next week, the 10th. So the 10th is your first exam. The exam is essentially going to cover chapter 1. So chapter 1 is technically 1.1 to 1.9. I don't think we're going to have time for 1.9, which is okay because it's not really, it's like we should cover it if we have the time, but if we don't have the time, it's okay to not cover. So I'm trying to cover 1.1 to 1.8. Oh, I should be clear, this is in Hughes-Hallett. I'm sorry. The other one kind of jumps around, and of course I always put the on the course content page, I always tell you what the other section of the other book is. And I'll put that in a bit more detail on the review packet, which I'll talk about in a second. Anyway, so this is technically 1.5. So we've got a couple more sections to cover, and this week we should be able to cover 1.5 through 1.7 with no problem. So we might need to take a little bit of Monday to cover 1.8 if necessary. Or if it's really getting too late. Oh no, I don't have those notes up on Blackboard. Oh no. I need to write that down before I forget. Sorry, there's a section missing in your notes on Blackboard. And if I don't write it down, I will forget. Oh, no, no, no. I would never put sections we don't cover on a test. Good Lord Almighty. Oh, no. If we don't cover it, it will not be on the test. That's the other thing. If it's taking too long this week and we can't even get to the end of chapter 1, I'll just, we'll finish chapter 1 after the exam, and the exam will just cover what we've covered so far. So anyway, towards the end of the week, there will be a review packet going up on Blackboard. It will tell you all of the sections that the exam will cover. It will tell you which sections from each book. And it will have a bunch of review problems as well. And so usually what I do is I put the blank review up for a day or two before I put up the answers, just so that you have time without the answers and it's not tempting to just look at the answer. You try it yourself. But that will be up towards the end of the week. I hope to take at least a part of Monday for a review, but if we need to spend Monday finishing up a little bit of content, we'll do that as well. But anyway, I'll probably talk about that again more towards Friday and Monday, but that's coming up. So you'll have your review packet up by the end of the week, and yeah, okay. So we're on to our notes labeled exponential functions. So this is 1.5 in Hughes-Hallett and 1.7 in the online book. So exponential functions. So at this point in time, all we've talked about is, well, I should be careful. all we've officially talked about is linear functions. The problem we just did dealt with a quadratic, but here is kind of our first look at the next official set of functions we're going to look at, exponential functions. So this says warm up, but we're going to go over it together. So here we go. So suppose you deposit $100 in a bank into a savings account. If you put your money in bank A, they will deposit an additional $10 into your bank account every year. Yeah, it does say per year. I missed it. And if you put your money in bank B, they will increase your balance by 10% per year. So essentially what we're going to do is we're going to look at the differences in the balances for the first 3 years. So how much money would you have after 1 year? Well, in bank A, if you started with 100 and they're just depositing an extra 10 bucks every year, so that at the end of the year they'd deposit an extra 10 bucks, not 10 ducks, $10. So you would end up with $110 in bank A. Now in bank B, you still start with $100, but they're going to add an extra 10%. Now that's 10% of 100. So 10%, remember, as a decimal would be 0.1. You move the decimal point 2 spaces to the left. So we're going to add 10% of 100, which would be equivalent to 100 times 0.1. So this will be 100 plus 10. So bank B will also result in $110 at the end of year 1. What about after 2 years? Well, for bank A, at the end of the first year, you had 110. So starting year 2, you have $110. Oh my gosh, I can't talk. At the end of the year, they're going to deposit $10, so you're going to end with $120. With bank B, you're still going to start with the 110. And now they're going to add on 10% of that 110. So in this case, we have 110 plus 11 plus. So you'll end with oh my gosh, with $121 in the bank. So it's only a difference of $1 so far, but I would take an extra $1 for free. At the end of 3 years, with bank A, you started with $120 in the 3rd year, and oh my gosh, they add on an extra 10, so you would end with 130. Bank B, you start with the 121 and add on 10% of 121, which would be 12.1. So you're going to end with $133.10. Still not a huge difference by any means, excuse me. But, you know, if you're just having it sit there and it's quote unquote free money, I would take an extra $3.10. So which bank should you use? Well, it looks like you should probably use bank B, because after the first year, you're getting more money. Now, at this point, it doesn't seem like a huge difference, but if you were to continue this on for many, many years, that difference would start to get much larger. And if you put this in for, 100 years, especially, somehow, even just after 10 years, it would be a pretty decent difference. But the longer you put it in, the bigger that difference is going to become. Now, bank A is essentially following a linear model, okay? So bank A is essentially following a linear model, and bank B is following an exponential model. Now, that's not exactly what exponential functions look like per se, because I'm about to write down the function and it doesn't have a plus sign in it. So it's not exactly the format of an exponential function, but it uses kind of the spirit of an exponential function where these values are changing by a certain percent or a certain factor over time. So if I can scroll, there we go. Now this definition box has a lot of information at once. Don't panic. It's a lot of information. Just don't freak out. So, and this is the probably biggest difference in notation between the two books, because, and I'll explain that in a second. So this definition and this notation would follow Hughes-Hallett, and I will show you how it reflects to a similar format in the other book. just to try to avoid confusion in case anyone's using the online book. So a function p is an exponential function of t with base a if it takes the following form. Whoops. P equals p naught a to the t. P naught is called the initial condition. Sometimes I'll call it the initial value just because I'm used to calling it that. The formal definition is initial condition. I don't like how that is up there. There we go. And A is the factor of P, is the factor P changes by as T increases by 1. Now A is called the base. So it's called the base, but what it actually means is it's the factor that P changes by when T increases by 1. Now the unfortunate overlap with the online book is that your online book uses a b to the x. And I just hate that the a is in the different spot. So here, the a is the initial condition. And the b is the base. Okay. So the one thing I definitely want to clarify is no matter which format you use, I don't care which format you use, the base has the exponent. I will almost never say base A or base B. I will just call it the base. So whichever format you use is perfectly fine. One thing has the exponent, the thing with the exponent is the base, the thing without the exponent is the initial condition. I usually default to this because this is what most people use. I don't see a lot of people using a b to the x. I see a lot of people using this format. So that's what I've been used to. So that's what I'm going to use. Now, again, this is kind of a side note. So when I say A, I mean the base here. So if A is greater than 1, if your base is a value greater than 1, we have something called exponential growth. If your A value is between 0 and 1, you have something called exponential decay. Notice that neither of those has an option for negative. A side note that I'm about to erase, so I wouldn't write it down if I were you. I'm just trying to clarify. Technically, functions like this can exist in life. Maybe I shouldn't even say life because they don't really have many contextual representations, but they exist in mathematics in general. We will not use them. Every single exponential function we encounter will only use positive a values. Okay, so I do want to specify that technically you could have negative a values in mathematics in general, but we're not going to use them. Our a values, our base is always going to be positive. Now, this a value, this base, is made up of 1 plus r, where r is the decimal representation of a percent change. Now, essentially, this was the 10%. What the heck is that? This was the 10% or the 0.1 in the problem we were just looking at. That's why it follows the spirit of an exponential function, is because it has this decimal representation of a percent change, and we were using that percent change to add on a certain amount every year. So our a value is made up of a rate. So also the wording of these questions is highly important. Okay, so if you see the word rate, it's giving you an r value. If you see the word factor, which you will see much less, but it's talking about the base. Okay, more often than not, you will be given the rate, not the factor. But we will see a couple problems of that in a couple minutes. Now, the r value can be positive or negative. So the r value can be negative, but our a value will always be positive. And this has a similar relationship to exponential growth and decay. So if r is positive, we have exponential growth. And if r is negative, we have exponential decay. And essentially all exponential growth and exponential, oh my gosh, all exponential growth and decay is trying to tell us is whether or not the values are growing or shrinking. When we get to 2 more sections from now in the exponential growth and decay section, we will have problems where they tell us whether it's growth or decay, and that essentially tells us the sign of the R value. Okay. And the most common base is the number E, which is approximately 2.71828, and it continues on forever, just like pi. This is called the natural base. Now, I bet you money that you can't find a mathematician that will ever use E as a variable. So if you ever see E in a problem, it is the number, not the variable. Unless it's specifically stated in the problem, let E be some variable value. But I have, in my life, never seen any mathematician or any book or anything use E as a variable, because everyone says that E is a number, because it is in math. Okay, anyway. So if you ever see an E, you can pretty much assume it's going to be the number E, not the letter. Well, not like representing just a letter. Anyway, so I know that's a lot of information at once. So now let's start diving into a couple of questions that are going to kind of unpack this a little bit. So the first thing we're going to look at, I'm going to leave this up while I kind of introduce the first question. So back when we were talking about linear functions, we had those questions where we were given a table and we wanted to know whether the table was linear. And we did those little loop-de-loop things and checked all the slopes to see if the slopes were the same. We want to now do the same type of thing, or develop a different type of process to determine if a set of data is exponential. So say we have this first problem, a new restaurant just opened, the table below gives some values for the number of customers on a day. Could this data be exponential? Why or why not? And so let me kind of write some notice stuff over here. Exponential functions have a constant factor. Linear functions have a constant slope. Exponential functions have a constant factor. So just like we had to find the constant slope, we have to find that constant factor. So here's the way you're going to find that constant factor. If the x, or t in this case, values are consecutive, you just calculate y2 over y1. Specifically, y2 must be with the larger x value. So unlike slope, this order matters. It always needs to be the y value associated with the larger x value on top. That doesn't necessarily mean the larger y value goes on top. In this case, it will. But in some situations, it's the smaller y value that goes on top. So it has to be the y value associated with the larger x value. Otherwise, you get into some hoopla that's really complicated and no one wants to deal with. It's not that complicated. Anyway, no, in this table, you don't need to draw these little loops, but I just want to drive it home. In this table, all of the data is consecutive. So we can just do this. I will show you what you do when it's not consecutive in a second. So what we would do here, since all of these are consecutive, we're just going to take consecutive t values and we're going to take the ratio of their y values. So in the first set from 1 to 2, we would take 18 divided by 14. And we would find what that is. So this is 1.286 approximately. And then you continue from 2 to 3. If we take that ratio, we'll have 24 divided by 18. This will be 1.3 repeating, essentially. I don't like the look of that 3. There we go. From 3 to 4, we would have 31 over 24. 1.292. Now let me squeeze it in here really quick. We don't even really need it at this point, but just to squeeze it in there real quick. The last piece between 4 and 5 would be 40 over 31. And I want to leave this space on the side for the next thing I want to talk about. 1 second. I don't have this in my notes, so I gotta calculate it. 48 divided by 31. 1.2903. Okay. What? I wanted you to change color. We're comparing these values. They're not the same number. Since they're not the same number, this is not consecutive. Not, oh my gosh, not exponential. The factor is not constant. Now, we do want to be a little careful here. If this one didn't exist, say it wasn't part of the data. If that one didn't exist, I would almost say that it is exponential. Now I know that those numbers aren't exactly the same, but notice how all the rest of them are approximately 1.29, right? So if they were all approximately 1.29, that would be enough to say it at least follows somewhat of an exponential relationship. Now, usually, more often than not, and this is the thing we're gonna take to be the rule for our class, is you would want the factor to match. And we're gonna say to 3 decimal places. So if that's my rule, then this still wouldn't be exponential even in this case. If we were saying we could take it to 2 decimal places, then we could get away with it. But I'm going to say the rule for our class is that we want the factor to match to 3 decimal places. If the factor matches at 3 decimal places, but then after the 3rd decimal place, it's all different, we will still take that to be an exponential function. Okay, that's what I mean by that. Because sometimes there's rounding things when people are taking their data and blah, 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 blah. So maybe they just round it instead of taking the full amount. And so we do give them that little bit of wiggle room, but we're going to make the wiggle room be after 3 decimal places matching. Okay. Now, what if these weren't consecutive? Which happens. If they're not consecutive, so one last piece of notes over here. So this is kind of a hefty problem we got going here. If X or T, but I'm just going to say X values to save space, are not consecutive, we have to root the factor by a root of the change in X value. And I will explain what I mean by that in a second. I'll just let you write that down real quick. Now, this also means that if you're given a table, you don't have to take consecutive X values. So I can actually, I'm going to do this process on the table that we have right here. So say I didn't want to take consecutive T values in this case because I didn't feel like it. And I wanted to go from 1 to 5, and I wanted to use those 2 points as my thing that I'm checking the factor for. So notice that our change in T here is 5 minus 1. It's a change in 4. You know, how far apart are those two numbers? So what you do in this case is very similar, as you still take a ratio of the Y values. So the Y value of 5 was 40, the Y value of 1 was 14. But we now have to take the 4th root of that. If you're trying to punch this into a calculator, the way I find to be easier is to make it a fractional exponent. So a root is equivalent to a fractional exponent. So the 4th root is equivalent to the 1/4 power. And if you did this, you would get approximately 1.3. Which again, if you were comparing it to all of these values, let me make sure that doesn't have a larger decimal on it. I don't trust my notes here. And 1/4 power. It's 1.300, so this, if you were to take this non-consecutive one, this would be compared to the other ones. So like it still just works the same way as that you're just comparing these values, but you don't necessarily have to take consecutive x or t values to be able to do so. Oh, so just like that definition, this question was packed with information. Are there questions on this question? So if you want to find if data is exponential, you have to look at a constant factor. Take factors of y values. If you don't have consecutive x values, you need to take a root. And the root, the number of the root, is going to be the difference between the x values. And we're going to take something to be exponential if all of the factors match up to at least 3 decimal places. Okay, I'll wait a couple more seconds in case anyone's still taking something down there. The next question is a bit less jam-packed. So, and we gotta, yeah. So we've got the grades of 6 students are given in the equation below, where time t is measured in weeks after the first exam. So we have a bunch of different equations to represent student grades. Alex's grade has been decreasing since the first exam. Which formula or formulas could represent her grade and why? So we want a decreasing function. Decreasing here is going to match with exponential decay. So in terms of this, what do we know that can tell us exponential decay? Well, it would either be the base value or the rate value. These equations are set up as our P naught a to the t situation. So, yep. And I'll actually just kind of leave that in there while I do this first question. So these questions are set up to have the a value there for us. So what we're going to be able to compare is we're going to be looking at our a value. Also try to go a bit slow in case you're taking something down from the last question. So exponential decay is when our a value is less than 1 but greater than 0. So essentially we're going to list all of the formulas that have a value, an a value less than 1. Which in this case would be the third one. The 72, 0, whoops, that was supposed to be a highlighter. 72, 0.9 to the t. This one, the fourth one, which is 0.99, which is just below 1. And then this sixth one. So we have the third one, the fourth one, and the sixth one are all options to represent Alex's grade because those all represent decreasing functions. And I'm gonna scroll back down now. And we're almost done class, so if you need to get that after class really quick, I can scroll back up again. Which student's grade is falling the fastest? So what is the grade that's falling the fastest? So we would essentially want, ooh, I need to be careful with the, I was about to phrase something very poorly. We need the largest decrease, and I almost didn't phrase it like that, but then I decided to. But the largest decrease is actually going to be related to the smallest base value, which in this case is an a value, but I just want to say base in case you're using the other form. So we want the smallest base. So what is the smallest base we have here? Well, the smallest base is the 0.98. That 89, I can't read. 0.89. So the smallest base would be the largest decrease, if you will. Essentially, the smaller the base, the more it's decreasing by each time. So if we want the thing that's falling the fastest, we want it to decrease more over time. And the smaller the A value, the more it decreases. Now we have Umar's grade has been rising since the first exam. Which formula or formulas could represent his grade and why? Well, I guess the why for the first one is because we're looking for exponential decay. That's kind of the reason. So the reason here is what we're going to be looking for is we're going to be looking for exponential growth. So I didn't really state it as a y, but that's essentially what the y is. So we're looking for a base value that's greater than 1. So we've got 3 options for this one too. We've got the 1.001, 1.05, and 1.03. All of those are greater than 1. All of those represent exponential growth. So all of those are functions that are growing and increasing over time. Let me try to zoom out so I can keep those values in there. There we go. Which student's grade is rising the fastest? So rising the fastest would be the largest increase. Now this one kind of matches. This would be the largest base value. Whoops. So which one of those has the largest base value? It would be the 1.05. So whoever student 2 is has the grade that's rising the fastest. Now, Karan came out of the first exam with an 85 in the class. Which formula or formulas could represent his grade? Now, let me unhighlight those. So an 85 on the first exam would mean that the initial value was 85. So which of these equations have an initial value of 85? There's 2 of them. There's the number 4 and the number 6. Because those are the only 2 with the 85 in the front, with the value that doesn't have the exponent attached to it is our initial value. So we have that this could be possibly option 4 or option 6. And I think that's the last. Yeah. So how we're changing over time is going to be the base value. It's going to be exponential decay if it's less than 1, exponential growth if it's greater than 1. If you want it to be the largest decrease, you're looking for the smallest, base value. If you're looking for it to be rising the fastest, you're looking for the largest. Why did I say B value? I meant to say base value. That's what I was writing. Base value. Down here, for some reason, I wrote B value because I think I got I got distracted mid writing and I only wrote B value. So maybe fix that if that might confuse you later. And then when we were specifically just looking for an exam amount for our initial value is, remember, the initial value is the thing without the exponent, the base value is the thing with the exponent. Only got 1 minute, which is obviously not worth taking the time to try another one. So before we leave, I will, I'll type out in chat. You have a quiz on Wednesday. What it will cover is it will essentially cover that last section. It will cover cost, revenue, profit, supply and demand, and possibly break even or equilibrium points. So when I say cost, revenue, and profit, I mean finding the cost, revenue, and profit functions. Supply and demand, I could ask you an question like you've seen a few of them on your homework was, here's some information, find the demand equation assuming it's linear. And then I could ask you break even or equilibrium points, or of course, then you either need to set things equal, well, break even, remember break even is profit is 0 or cost is equal to revenue. And then equilibrium is for when supply equals demand. So it's essentially that last set of notes that your quiz on Wednesday will cover. So we'll go over warm up on Wednesday to cover that. We'll continue more of these notes, and then we'll keep going. So if you have questions, feel free to stick around for a little bit. Otherwise, I will see you on Wednesday, and have a good day. Yeah, I'm still holding office hours today, so I'm gonna go grab lunch, but then at 1:30 I will pop into ooh, are you talking in person or virtual? Because I can hop into my virtual office hours at 1:30. Online? Yeah, no, I'll be there. Okay, I don't need to rush into my office. So at 1:30 I will be in my little online office hours after I snag some lunch. So feel free to come meet me there if you need.